11D. In 1937, the Stanford Binet IQ test was re-standardized with two forms, L and M. A large number of subjects took both tests. The results can be summarized as follows. L average is 100, SD of 15. M is an average of 100, SD of 15. R equals 0.8. And by the way, that's always true on the IQ test. By definition, 100 is the average, and 1 SD is called 15. So if people 100 years ago were smarter than we are now, the average is going to be the same, because that's how the IQ test works. Is the average is always 100 and the SD is always 15. So A, true or false and explain. The regression line for predicting the scores on form M from the score on form L has an RMS error of about 9 points. How do we calculate the RMS error? Well, we take, I can get rid of this. We take the SDY and we multiply it by the square root of 1 minus R squared. So my SDY is 15 times the square root of 1 minus 0.6 squared. Oh, is it 0.8? Oh, sorry. 0.8, thank you. So 1 minus 0.8 squared. And I get 9. So, true. Suppose the scatter diagram looks like 1 below. If someone scores 130 on the form L, the regression model predicts 124 for the score on form N. What do we call that? Regression effect. 130 got turned into 124. True or false? This prediction is likely to be off by 9 points or so. True. True. So what this is getting at is, if I randomly select a y value, my best guess for the y value is 100. How far off am I going to be? 15 SDY. So a randomly selected y value would be 100, and we would expect to be off by about 15 points. Okay? If I know the x value, so if I know the x value is 130, that gives me a prediction for y. What's my best guess for a y value if I know that x is 130? Well, I go up on the regression line, and I get 130, 124. My best guess is 124. Is that expected to be off by the SDY of 10? No, because there is less variation in this column than there is in the y-axis total. How much variation is there? The RMS error, 9. So 24 plus or minus 9. Now, Megan asked a good question a minute ago, and she said, is that true for every column? And the answer is yes. The SD of that column is 9. And the SD of this column is 9, and this column is 9, and this column is 9, over and over and over. And when I combine all of those SDs with 9, the RMS error essentially is what it is, and the total turns into, this is not 10, it's 15. Okay. So B. Suppose a scatter diagram looks like, nope, C. Repeat if the scatter diagram looks like 2. What do we do for 2? So for 2, so I have this. Okay, and here's my point of averages. If I go over here to 130, and this is 130, 124, how much variation is there in this column? A lot. Is it going to be 9? No, it's more. Now, how much variation is there over here? Not very much. So this one is probably a lot more than 9, and this one is a lot less than 9, and because the graph is not football shaped, our rules don't apply. So that would be false. Okay, 2. The data in figure 8 can be summarized as follows. So x bar equals 68, SDX is 2.7, y bar is 69 with an SDY of 2.7, and r equals 0.5. Find the RMS error of the regression line for predicting son's height from father's height. So I need to take my SDY, 2.7, and multiply that by the square root of 1 minus 0.5 squared. Times the square root of 1 minus 0.5 squared. And I get an RMS error of 2.3. If a father is 72 inches tall, predict his son's height. Well, if the father is 72 inches tall, how do I predict the son's height? Well, I have to figure out how much taller he is. So 72 minus 68 equals 4. Divide that by 2.7. So 4 divided by 2.7. And this is essentially a z-score for the x. So he is 1.48 SDs taller than average. And now I need to multiply that by my SDY, which is 2.7, and my R value, which is 0.5. So this number times 2.7 times 0.5 to what? 2 inches above average. So what do I do with that 2? I add it to the 69 and I get 72,71. So if the dad is 72 inches tall, we expect the son to be 71 inches tall. Okay? How far off are we expected to be on that 71? This right here, 2.3 inches. Is that the next question? Yeah, this prediction is likely to be off 2.3 inches or so. And repeat the step for a father that is 66 inches tall. So hopefully you're getting good at this. 66 minus 68 is negative 2. That is inches. Divide that by 2.7, and I will get the z-score for the x's. So negative 2 times 2, negative 2 divided by 2.7. Now, if I were actually doing this, I wouldn't even bother multiplying by 2.7. Why is that? Because you divide by 2.7 and then you times by 2.7 because the SDs are the same. So that gives me 0.74 negative. So this is how many SDXs that person is below average. That is a z-score for the x's. So I take that negative 0.7.4 and I multiply it by the SDY, which is 2.7, and the R value. So times 2.7, and I'm going to put a negative in there so I get the right. And I get negative 1. Wait a minute. That's right. No, wait a minute. Oh. So negative 1 what? Oh, that's inches. That's right. I was confused. I thought it was SD there for a second. So this is 1 inch below average, so I take the 69 and subtract 1, and I get 66,68. If the dad is 66, then the son is expected to be 68. Okay? And that score is likely to be off by 2.3 inches. Okay? 3A and B. maybe that's not going to work today. So, average education 13, SD 3.4, average income 18, SD of 20. Find the RMS error for the regression line for predicting incomes from education. So we're going to take 20,000 and times that by the square root of 1 minus 0.37 squared. And I get 18,580. Okay. B, predict the income of a woman with 16 years of education. Well, I take 16 and I subtract the average, which is 13, and I get 3. Divide that by 3.4. And I get 0.88. So this is kind of like a ZX. That's how many SDXs I am above average. Now I need to multiply that by the SDY, which is 20,000. So times 20,000. And times it by 0.37, which is the R value. And I get 6529. What does that mean? That's how much more we expect this woman to earn than average. So I add it back to 18,000. Oops, that's not what I wanted. We want this plus 18,000. And she's expected to earn $24,529. How far off is that going to be? The RMS error right there. Now, just looking at that data, would we expect this to be football shaped? Just looking at the numbers on page 193, are there any red flags? The R value is terrible. Okay, that's not good. But there's something else going on that's even worse. The SD of the Y's is larger than the average of the Y's. So if we go out one SD to the left, we actually capture everything on the left side. And if we go out one SD to the right, we're not going to capture as many. And if you look at the chart on page 192, is that football shaped? Not even close. So do we expect this prediction we just made of 24,529 to be very accurate? Well, look at the chart. Go to 16 years. What does the average look like for that 16 years? Well, and remember, average is weighted, so the people on the top end are going to pull harder than the people in the middle. The average of that column is probably $30,000 or $40,000 because those outliers at the top skew the average in that direction. So in this case, the regression line does not do a good job at all. So, and the reason is because the people on the high end yank that average further. So we have a graph where here's the regression line, and the shape of the graph looks something like this. And we're looking at this column here. Well, if we cut those people off, then the average would be right there. But when we add those people in, that's going to pull the average above the regression line. So the 0.37 is a problem, but the graph is not even remotely football shaped. You know, it looks like a tidal wave. Not good. So we probably would not use linear regression to describe this.